72 hours ago, the European Space Agency released what they called the closest view yet of 3I Atlas, the interstellar object that's been captivating and terrifying the world in equal measure, billions of dollars in space technology. 7 Mars orbiters positioned for the shot of a lifetime. And what did we get? A fuzzy white dot that looks like someone sneezed on a camera lens. Within minutes, social media erupted, not with wonder, but with rage. Amateur astronomers with backyard telescopes were capturing sharper images of comets millions of miles farther away. And yet NASA, with its Mars Reconnaissance Orbiter, equipped with the most powerful camera ever sent to another planet, has gone completely silent. The government shutdown excuse? It's wearing thin. Especially when you realize that the Chinese and UAE orbiters are also mysteriously quiet. By the time you finish listening to this, 3I Atlas will be less than a week away from disappearing behind the sun, hidden from every telescope on Earth, during what should be its most active moment. And if Harvard physicist Avi Loeb is right, what happens next could change everything we thought we knew about what's possible in our cosmic neighborhood. If you're as fascinated by this mystery as I am, hit that like button and subscribe to stay updated as this story unfolds in real time. Tell me in the comments where you're listening from, what time it is there, and whether you think we're being told the complete truth about 3I Atlas. And if you want to help our community grow, share this on X, Facebook, Reddit. Thank you for always having our back. October 7th and 8th, 2025 will be remembered as the moment the space community collectively lost its patience. For months, we'd been building toward this. 3I Atlas, only the third confirmed interstellar object ever detected passing through our solar system, was making its closest approach to Mars. 7 different spacecraft from 4 space agencies were positioned to capture unprecedented images. The hype was real. Scientists promised us clarity, answers, maybe even proof of what this thing actually is. And then, the images dropped. The European Space Agency's ExoMars Trace Gas Orbiter, positioned just 30 million kilometers from 3I Atlas on October 3rd, released a series of images that can only be described as profoundly underwhelming. A fuzzy white dot moving slowly across a star field. No detail, no structure, nothing that would help us understand whether we're looking at a natural comet or something far stranger. The backlash was immediate and savage. Astronomy Vibes, a popular space commentary account on X, posted a side-by-side comparison that went viral within hours. On one side, a crisp, detailed image of Comet Lemon captured by an amateur astrophotographer with a simple mirrorless camera. On the other side, the ESA's image of 3I Atlas. The caption read, "If a simple mirrorless camera can catch Comet Lemon, why can't NASA capture 3I Atlas passing close to Mars?" The post currently has over 40,000 reposts. But it was the follow-up that really struck a nerve. Billions in funding, and this is the best photo they've got. Looks more like a weather balloon in a foggy backyard. To understand why people are so angry, you need to understand what we were expecting versus what we got. The CASIS camera aboard the ExoMars orbiter has an angular resolution of 11.36 microradians per pixel. At 30 million kilometers, that translates to 340 kilometers per pixel. Meanwhile, the estimated nucleus of 3I Atlas is only 5 to 46 kilometers across. That means the entire solid core of this object, at best, would occupy a fraction of a single pixel. And here's the kicker. ESA knew this. They knew their cameras were designed to photograph the bright Martian surface from a few hundred kilometers away, not faint objects tens of millions of kilometers distant. Nick Thomas, the principal investigator for the CASIS camera, admitted as much in the official statement. This was a very challenging observation. The comet is 10,000 to 100,000 times fainter than our usual target. So why release images they knew would be inadequate? Why build up expectations for months only to deliver something that provides zero new information? The official story is that they released what they had, that these are the best possible images from the available equipment. But the timing feels deliberate, almost like a pressure release valve. Give people something. anything, to look at while the real data stays locked away. Because, make no mistake, there are better images, much better images, and they're being held back. While ESA was taking flak for its fuzzy dots, NASA's Mars Reconnaissance Orbiter was capturing something entirely different. The HiRISE camera, short for High Resolution Imaging Science Experiment, is the most powerful camera ever sent to another planet. Its resolution is so precise that from Mars' orbit, it can distinguish objects the size of a kitchen table on the surface. When 3I Atlas made its closest approach to Mars on October 3rd, HiRISE had a resolution of approximately 30 kilometers per pixel at the object's distance. That's more than 10 times better than what the ESA cameras achieved. If there's any structure, any unusual features, anything that doesn't fit the natural comet narrative, HiRISE would have seen it. Avi Loeb, the Harvard physicist tracking 3I Atlas, put it bluntly in his latest blog post. The brightest pixel in the HiRISE image will provide the best constraint on the area of 3I Atlas. We are all hoping the HiRISE team will release their images as soon as possible. That was written on October 7th. It's now October 8th. Still nothing. The official explanation? The United States government shutdown. Over 15,000 NASA employees, more than 80% of the agency's workforce, have been furloughed. NASA's website isn't being updated. Public communications have ceased. It's bureaucratic paralysis at the worst possible moment. But here's what doesn't add up. ESA released their images. They're a European agency, completely unaffected by American political dysfunction. China's Tianwen-1 orbiter was also positioned to observe 3I Atlas, also silent. The UAE's Hope orbiter, equipped with the Emirates E-Exploration Imager, also had a clear shot. Nothing. Multiple space agencies, multiple sovereign governments with completely separate bureaucracies and priorities, all simultaneously unable or unwilling to release their best data on the most scientifically significant object to visit our solar system in years. The pattern is hard to ignore. Social media is ablaze with speculation. Some say it's coordination. Others say something was seen that requires careful review before public release. The more conspiracy-minded suggest the images show something so anomalous that releasing them without proper context would trigger mass panic. That last theory sounds absurd, until you remember what's been happening this past week with amateur observations. Because while the professional space agencies have been silent with their data, backyard astronomers have been capturing images that raise more questions than they answer. On October 3rd, the exact day 3I Atlas made its closest approach to Mars, a Portuguese amateur astronomer under the username Dobsonian Power uploaded an image that immediately went viral. Using only a solar telescope from his backyard and some aggressive digital enhancement, he captured what appears to be an angular structure inside 3I Atlas, dark geometric shapes, protrusions that don't match the typical diffuse glow of a comet. The caption he added was simple, but loaded with implication. What on earth is it? Within 6 hours, the image was shared across every major astronomy forum, subreddit, and social media platform. The reaction split into two camps almost instantly. One group saw clear evidence of artificial structures, proof that 3I Atlas is not what mainstream science claims. The other group dismissed it as classic pareidolia, the human tendency to see patterns where none exist, amplified by processing artifacts from inappropriate equipment. The debunkers had solid, technical arguments. Solar telescopes use specialized filters designed to observe the sun's extreme brightness, not faint, deep space objects moving at interstellar velocities. The equipment simply wasn't built for this. Add aggressive digital enhancement to compensate, and you're essentially asking an algorithm to invent details that aren't really there. But here's where the story gets complicated. Dobsonian Power isn't some random internet conspiracy theorist with a cheap telescope. He's a respected amateur astronomer who has been sharing legitimate astrophotography work for over a decade. His YouTube channel documents his equipment, his methods, his image processing. This isn't someone trying to manufacture evidence for clicks. And when pressed on the anomalous structures, he didn't double down with wild claims. Instead, he acknowledged the uncertainty. His cautious, scientific response makes the reaction to his image even more telling. Within 24 hours, multiple websites published articles specifically debunking his capture. The timing felt coordinated. The tone felt defensive, as if someone needed to quickly establish the narrative that nothing unusual had been photographed. And then the enhancement wars began. Users on Reddit and Twitter started downloading the original ESA images and running them through their own processing algorithms. Some used standard astronomical stacking techniques. Others used AI upscaling tools. The results were wildly diverse. Some just showed sharper versions of the same fuzzy dot. Others revealed what appear to be distinct geometric patterns, edges, structures that seem too regular to be natural ice and rock. The problem is, once you aggressively process an image, especially with AI, you're no longer looking at what's really there. You're looking at what an algorithm thinks should be there. But the proliferation of these enhanced images muddied the water, making it nearly impossible to distinguish between legitimate amateur observation and outright fabrication. Within 48 hours of the ESA photo release, dozens of enhanced versions were circulating. Some showed metallic surfaces. Others depicted what looked like solar panels. Most were obviously fake, but mixed in were a few images that felt different, more subtle, showing just enough unusual regularity to make you wonder if something real was being obscured. On October 4th, an anonymous user on 4chan's divided by X divided by board posted what they claimed was insider information about 3I Atlas. The post was titled ESA Data Leak and began with a credential claim just specific enough to sound legitimate, but vague enough to maintain anonymity. I am a doctoral researcher working with the European Space Agency with continuous access to the combined observational data of 3A Atlas. Internet leaks are a dime a dozen. Most are easily dismissed. But this one was different. The level of technical detail was unsettling. The poster didn't make wild claims about alien invasions. Instead, they laid out a series of specific observational anomalies that, if true, would fundamentally challenge our understanding of 3I Atlas. Anomaly 1. Chemical impossibility. According to the post, spectroscopic analysis shows 3I Atlas is releasing to 100 kilograms of nickel gas per second, but with almost no iron emission. In normal stellar and planetary chemistry, nickel and iron are inseparable twins. They form together in supernovae. Finding abundant nickel with virtually no iron is like finding smoke without fire. Anomaly 2. Thermal contradiction. The object is releasing massive amounts of gas and dust, the signature of an active comet being heated by the sunday. But infrared observations show it remains cold, far colder than it should be. The poster compared it to watching someone sweat profusely in a freezer. The physics don't match. Anomaly 3. Trajectory precision. The post referenced what Avi Loeb has been saying publicly, that 3I Atlas's orbit is inclined at only 4.89 degrees. But the 4chan poster added something. The trajectory isn't just unusual. It's a perfect straight shot from the direction of the galactic core. No wobble, no deviation, as if it was aimed. Then came the part that elevated this to something darker. The poster claimed the object fits the profile of what they called a post-biological entity. Not a comet, not a conventional spacecraft, but something in between. They described it as having a 3-phase particle engine with an estimated output of 75 megawatts, continuously transmitting an active signal and probing our solar system. The post concluded with a theoretical framework. The poster suggested 3I Atlas might be a macroscopic quantum object, specifically a cue ball. It's an exotic theoretical construct from particle physics that, if stable, could have properties that seem impossible under normal physics. It could be incredibly dense while appearing diffuse. It could absorb and redistribute energy instantly, explaining the thermal contradictions. It could even explain the nickel without iron problem. Within 18 hours, the post was screenshotted and shared across Reddit and UFO forums. The conspiracy subreddit thread discussing it accumulated over 2,000 comments before moderators locked it. But locking the thread didn't stop the conversation. It just moved it to other platforms. On October 4th, NASA's Perseverance rover, sitting in Jezero crater on Mars, captured something in the night sky. The image from its right navigation camera showed an elongated streak of light, about 4 times longer than it was wide. At first glance, it looked like a typical long-exposure capture of a moving object. Comets and asteroids often appear as streaks, standard stuff, except the math didn't add up. When people started calculating the apparent size of the streak based on Perseverance's known camera specifications and the distance to 3I Atlas at the time, they arrived at a disturbing number, 50,000 kilometers long. That's not a comet nucleus. That's not even a comet with a tail. That's something else entirely. For comparison, Earth's diameter is less than 13,000 kilometers. If this streak represented the actual physical size of 3I Atlas, we were looking at an object nearly 4 times wider than our entire planet. Social media exploded. Was 3I Atlas actually a massive cylindrical craft? Had it been hiding its true size all this time? The timing seemed significant. This image emerged just 1 day after the Mars flyby, right when all the professional space agencies went quiet. Speculation reached such a peak that Representative Anna Paulina Luna, a member of Congress, reached out directly to Avi Loeb for his analysis. Think about that. A sitting member of the US House of Representatives felt compelled to contact a Harvard physicist about a photograph from Mars. That's not normal protocol. Loeb's response was thorough and, on the surface, reassuring. He calculated that the Perseverance navcam has a resolution of 0.3 milliradians per pixel. At a distance of 38 million kilometers, that translates to about 12,500 kilometers per pixel. The streak in the image spans about 4 pixels, which gives you that 50,000 kilometers number. But Loeb argued this was an artifact of composite imaging. The streak wasn't the actual size of 3I Atlas. It was the path the object traced across the Martian sky during a long exposure time, likely about 10 minutes of stacked images. His reasoning was solid. 3I Atlas was moving relative to Mars at over 90 kilometers divided by second. Over 10 minutes, that's exactly 54,000 kilometers of travel, perfectly matching the streak length. The shape wasn't the object. It was the object's motion smeared over time. Case closed, right? Except Loeb included one sentence in his analysis that conspiracy theorists latched onto like a lifeline. He wrote, "If the navcam images represent single snapshots with an exposure time below 3.28 seconds, then the observed source is not 3I Atlas. In that case, the source might be much closer to the camera. Wait, if these are single frames, then what Perseverance photographed wasn't 3I Atlas at all. It was something else, something closer to Mars. That qualifier opened a door that no subsequent clarification could fully close. Because NASA hasn't confirmed if the image is a composite or a single frame, they haven't released the metadata. The government shutdown excuse applies here too. No staff to process requests. The 15th of August, 1977, Ohio State University's Big Ear radio telescope detected a 72-second burst of radio energy so unusual that astronomer Jerry Eamon circled it on the printout and wrote one word in red pen: wow. For nearly 5 decades, that signal has remained one of the greatest mysteries. It came from the direction of Sagittarius. It was narrowband, focused at one specific frequency, and it has never repeated. Hundreds of follow-up observations, thousands of hours of listening, nothing, just that one burst 48 years ago. And then, eternal silence, until Avi Loeb ran the numbers on 3I Atlas. He calculated where the object was on the 12th of August 1977, just 3 days before the WOW signal was detected. The answer, about 600 astronomical units from Earth. But more importantly, he calculated the direction 3I Atlas was coming from at that time. Right ascension, 19 hours 40 minutes. The WOW signal came from 19 hours 25 minutes. The two directions are separated by only about 9 degrees. In the vastness of space, with random objects coming from any direction, the probability of this alignment is about 0.6%. Not impossible, but deeply suspicious. Loeb didn't stop there. If 3I Atlas sent the WOW signal from 600 AU, how powerful would the transmitter need to be? The math is simple. It corresponds to a transmitter output between 0.5 gigawatt and 2 gigawatts. For reference, a typical nuclear reactor on Earth produces about 1 gigawatt. So, we're talking about nuclear power plant levels of energy, focused into a narrow radio beam. Entirely reasonable if you're trying to send a detectable signal across interstellar distances. There's one more detail that makes the connection hard to dismiss. The WOW signal was observed at 1,420.4556 megahertzes, blue shifted by about 10 kilometers per second relative to the hydrogen line. That blue shift indicates the source was moving toward us. 3I Atlas is currently approaching the Sun at about 60 kilometers per second. Loeb suggests that if this object has maneuvering capability, it could have been moving slower in 1977, then accelerated after detecting habitable planets in our solar system. A reconnaissance pulse. Here's what makes this whole connection so frustrating. It would be trivially easy to check. Point a radio telescope at 3I Atlas. Listen at the hydrogen line frequency. If it's transmitting, we'll know within hours. And yet, as Loeb noted in his latest blog post, not a single radio telescope has reported data on 3I Atlas. The Very Large Array, VLA, hasn't looked. The Green Bank Telescope hasn't published observations. Even SETI, the organization dedicated to finding extraterrestrial signals, hasn't publicly announced any monitoring efforts. The silence from the radio astronomy community is deafening. Imagine throwing a dart at a globe from across a room while blindfolded. Now imagine that dart not only hits the globe, but lands within a few degrees of the equator. That's roughly the statistical improbability we're dealing with when we look at how 3I Atlas entered our solar system. Objects coming from interstellar space can arrive from any direction. They should be randomly distributed across the celestial sphere. And yet, 3I Atlas arrived with an orbital inclination of just 4.89 degrees relative to Earth's ecliptic plane, less than 5 degrees. This puts it in less than 1% of all possible arrival angles. Avi Loeb has been hammering this point in every interview, every blog post. The trajectory is anomalous, not just unusual, but statistically profoundly unlikely for a random interstellar object. Why? Stars in the Milky Way have random motions. That randomness means objects ejected from other star systems should arrive at our solar system from all directions. There's no preferred direction, no cosmic highway that funnels interstellar visitors into our ecliptic plane, and the galactic disk itself is tilted about 60 degrees relative to our ecliptic. If this object came from a typical star system, we'd expect it to arrive at a steep angle, not a shallow one. Compare 3I Atlas to the other interstellar objects. Oumuamua, discovered in 2017, arrived with an inclination of 123 degrees wildly tilted. 2I, divided by Borisov, spotted in 2019, had an inclination of 44 degrees still steep, still consistent with random arrival. Both of those objects behaved as expected. 3I Atlas is the outlier, the anomaly. Now, layer that on top of everything else. The WOW. Signal alignment also less than 1% probability. The chemical anomalies with nickel but no iron. The thermal contradictions. The missing high-resolution images from multiple space agencies. The government shutdown happening at the exact moment we need NASA most. Any single one of these could be explained away as coincidence, measurement error, or bureaucratic incompetence. But when you start stacking anomalies, when you start multiplying small probabilities together, the compound improbability becomes harder to dismiss. Something strange started happening around October 5th. Users across multiple platforms began reporting that their posts about 3 Eye Atlas were disappearing, not being flagged, actually vanishing. A Reddit user documented posting a detailed thread analyzing the chemical anomalies from the ESA leak. The thread gained traction, then it was gone. When the user tried to repost, the submission wouldn't go through. Shadow banned. On Twitter or X, other accounts noticed the same. Astronomy Vibes, the account that went viral criticizing the ESA photos, reported significant engagement drops after October 7th. Posts that would normally reach tens of thousands were suddenly plateauing at a few hundred views. No official restrictions, just algorithmic suppression, quiet enough to be deniable, but aggressive enough to be effective. YouTube presented a different problem. Content creators who posted analysis videos speculating about 3i Atlas began receiving demonetization notices. The stated reasons varied, discussing sensitive topics, potentially misleading content on scientific matters, or content that may not be suitable for all advertisers. The pattern was clear. You could make a video saying 3i Atlas is definitely just a comet. That was fine, monetized. But suggest there might be anomalies worth investigating. Suddenly, your video becomes advertiser unfriendly. Facebook's approach was the most overt. Its fact-checking system began aggressively labeling 3i Atlas content. Posts sharing the 4chan leak got slapped with missing context warnings. Claims about the trajectory anomalies were flagged as partly false, even when the posts were just quoting Avi Loeb's published calculations verbatim. The fact-check articles offered reassurance. Experts say unusual features likely natural processes. The subtext was clear: don't worry, don't speculate, trust the authorities. All of this ramped up within 48 hours of the ESA photo release, right as public frustration was peaking. It's the Streisand effect in real time. The more the content got suppressed, the more people assumed there was something worth hiding. October 29th and 30th. Mark those dates. In less than 72 hours, 3i Atlas will reach perihelion, its closest approach to the Sunday. For a natural comet, this is the moment of truth. The intense solar radiation should cause dramatic outgassing, possibly even fragmentation. But here's the problem. We won't be able to see it. 3i Atlas will be on the opposite side of the Sun from Earth. Every ground-based telescope on our planet will be useless. The object will be lost in the solar glare, completely hidden from observation during what should be its most revealing moment. Some call it unfortunate timing. Others see it as suspiciously convenient. Avi Loeb has been explicit about what happens next. In his October 3rd blog post, he laid out two scenarios. If it's a natural comet, it may erupt or break apart. But then Loeb added the alternative. If it is technological, it may maneuver to take advantage of the Sun's gravitational assist, or release probes that could intercept the Earth or other planets. Read that again. Release probes that could intercept the Earth. He's not talking about passive observation anymore. He's talking about active deployment. From behind the Sun, hidden from our view, it would be trivial to launch something toward Earth that wouldn't be detected until it was already close. Loeb went further. He wrote, if 3i Atlas maneuvers towards Earth when it reappears on the other side of the Sun, the financial markets may crash. The financial markets may crash. That's not a metaphor. He's suggesting that if this object demonstrates technological capability, the economic and social consequences would be immediate and severe. The timing of everything compounds the tension. The government shutdown means NASA is offline during the critical observation window. The best images from the Mars flyby are still unreleased. Amateur astronomers can't observe the object for the next month. We are flying blind into the most important moment of this entire encounter. There is one group watching. The Galileo project, led by Loeb himself, is operating 3 observatories. During late October and early November, all 3 will be in maximum operational mode, monitoring the skies. If 3i Atlas releases probes, the Galileo instruments might catch it. Might. early November. That's when 3I Atlas will emerge from behind the Sun and become visible again from Earth. Ground-based telescopes will be able to track it once more. We'll see if it survived perihelion intact or broke apart. We'll measure its trajectory to determine if any course corrections occurred. And we'll finally know if the past 4 months of speculation, conspiracy theories, and unanswered questions were justified, or just collective hysteria over a completely natural interstellar visitor. If 3I Atlas emerges on the same trajectory, if it shows clear signs of fragmentation, if it behaves exactly like 2I divided by Borisov did, then the mystery is essentially solved. A natural comet. Unusual chemistry, sure. Statistically unlikely trajectory, granted. But ultimately, just an icy remnant from another star system. The wow. Signal connection becomes coincidence. The 4chan leak becomes creative fiction. The missing NASA images become bureaucratic delays. Everything slots back into the comfortable framework where interstellar objects are interesting but not alarming. But what if it doesn't? If 3I Atlas emerges with an altered trajectory, if it demonstrates even subtle course corrections, if radio telescopes finally point at it and detect structured transmissions, if the NASA images eventually surface and show geometric structures, then we are in completely uncharted territory. Not just scientifically, socially, politically, economically, every assumption about our place in the cosmos gets challenged. Avi Loeb created what he calls the Loeb scale, a ranking system for how likely an object is to be artificial and how much of a threat it represents. Rank 1 is almost certainly natural. Rank 10 is definitely artificial with hostile intent. He has stated publicly he won't rank 3I Atlas lower than a 2. Even in the best-case scenario, the anomalies are too persistent, too numerous. A 2 means probably natural, but with enough unexplained features to warrant serious investigation. That's where we are right now, suspended between a probable natural object and a possible technological artifact, waiting for November, waiting for the high-resolution images that may never come, waiting for radio observations that haven't happened. ESA has announced that their Jewish spacecraft will observe 3I Atlas between November 2nd and 25th, right after perihelion, but the data won't be available until February 2026 due to communication delays. 7 months of waiting for images captured in November. 7 months of not knowing. 7 months of wondering if that fuzzy dot ESA showed us was really the best they could do, or if they're carefully managing a revelation they don't know how to deliver. Whatever 3I Atlas is, whatever it does, the conversation around it has already revealed something important about our civilization. We don't trust our institutions to tell us the truth about something this significant. We don't believe the official reassurances. We see patterns in the timing of shutdowns and data delays. We're primed for conspiracy because we've learned, sometimes the hard way, that conspiracy is not always theory. Sometimes it's just early reporting on what later becomes confirmed fact. Script 2 starts. On October 1st, 2025, something the size of a giraffe passed between Earth and our satellites. It came closer to our planet than the International Space Station orbits. We had no idea it was coming. By the time astronomers spotted it, asteroid 2025 TF had already gone, slipping back into the darkness of space like a shadow that forgot to announce itself. Think about that for a moment. We live in an age where we can photograph distant galaxies. Yet, a rock close enough to practically scratch our atmosphere went completely unnoticed until it was already in our rearview mirror. If you find that as unsettling and fascinating as I do, consider liking and subscribing to stay updated on these cosmic close calls. Tell me in the comments where you're listening from, what time it is, and whether you think we should be more worried or more amazed by how much we still miss. And if you want to help our community grow, share this video. Thank you for always having our back. The asteroid measured somewhere between 1 and 3 meters wide, small enough that had it entered our atmosphere, it would have burned up as a brilliant fireball. Nothing that would threaten cities. But here is what keeps astronomers awake at night. If we cannot reliably detect something this close, moving at speeds that would cross from New York to Los Angeles in less than a minute, what else might we be missing? The European Space Agency and NASA track thousands of near-Earth objects. To be classified as potentially hazardous, an asteroid must be at least 140 meters in diameter and come within 7.5 million kilometers of Earth, about 20 times the distance to the Moon. Asteroid 2025 TF falls far short of that size, which is partly why it evaded detection. Our survey systems prioritize finding the big ones, the civilization enders. But this tiny visitor reminds us that space is not empty. It churns with debris, ancient fragments from the formation of our solar system. Most of this material stays far away in the asteroid belt, but gravitational interactions, the subtle tug of Jupiter, can shift these orbits, sending rocks on new trajectories that sometimes intersect with ours. What makes 2025 TF particularly interesting is not just that it came close, but that it came close during a month when the sky seems unusually busy with visitors. While one cosmic traveler slipped past us unannounced, another is making a much more theatrical entrance. Comet C, divided by 2025 A6, better known as Lemon, is brightening in our October skies. Astrophotographers around the world have been capturing increasingly dazzling images as this ball of ancient ice and dust makes its way toward Earth. Unlike the stealth asteroid, Lemon has been tracked carefully. Right now, it sits at the edge of naked eye visibility. In the next few weeks, if skies are dark enough, you might be able to step outside and see it yourself. A faint smudge of light with a ghostly tail stretching away from the Sunday comets are fundamentally different from asteroids. If asteroids are rock, comets are dirty snowballs containing frozen water, carbon dioxide, ammonia, mixed with dust and organic compounds, the chemical building blocks of life. As a comet approaches the sun, the ice sublimates, turning directly from solid to gas. This creates the coma, a temporary atmosphere, and the solar wind pushes it into the characteristic tail. Lemon isn't the only comet. Another visitor, C divided by 2025 R2, known as Swan, also slides past Earth later in October. Both currently shine at around magnitude 6, the threshold of human vision. But comets are notoriously unpredictable. They can suddenly brighten or fragment. What draws us to them, beyond their beauty, is their connection to deep time. The ice in these objects formed billions of years ago. When we see a comet, we are seeing material that existed before Earth had oceans, before the Moon was fully formed. Some scientists believe comets delivered a significant amount of water to early Earth. Others suggest the organic molecules in them, including amino acids, may have seeded our planet with the raw materials needed for life to begin. This connection between ancient comets and the origin of life brings us to another discovery that has scientists reconsidering how common the ingredients for life might be. Chapter 3. A Nursery for Moons. 625 light-years from Earth, something remarkable is happening. The James Webb Space Telescope has captured the first direct measurements of a moon-forming disk, a rotating ring of gas and dust surrounding an exoplanet called CTRB. And within that disk, Webb detected the chemical signatures that could give rise to moons: hydrogen cyanide, acetylene, benzene, carbon dioxide, all carbon-rich molecules swirling in a structure that looks hauntingly familiar to planetary scientists. This matters because for decades, we've theorized about how moons form, but we've never actually watched it happen. Jupiter's 4 largest moons, the Galilean satellites, orbit in a flat plane, suggesting they condensed from a similar disk billions of years ago. 2 of those, Ganymede and Callisto, are 50% water ice. And now, with CTRB, we can see a similar process unfolding in real time. Of course, real time in astronomy means the light we see left 625 years ago. The planet is only 2 million years old, still accreting material. We are seeing a system in its infancy, a planetary nursery. What surprised researchers most was the stark chemical difference. The moon-forming disk around the planet, CTRB, is rich in carbon-bearing molecules, but shows no signs of water. Meanwhile, the planet-forming disk around the parent star does contain water, but lacks the rich carbon. This chemical segregation happened in just 2 million years. The implications stretch beyond understanding how moons form. If we can map the chemistry of these disks, we can predict which exoplanets might host moons suitable for life. In our own solar system, some of the most promising places to search for life aren't planets, but moons. Jupiter's Europa likely has a liquid water ocean beneath its icy crust. Saturn's Enceladus shoots geysers of liquid water into space from an underground ocean, and within those, we've detected organic molecules. If moons around other stars form with similar characteristics, the number of potentially habitable worlds in the galaxy multiplies dramatically. The United Nations has designated 2025 as the International Year of Quantum Science and Technology, marking 100 years since the initial development of quantum mechanics. It's fitting timing because 2025 is shaping up to be the year quantum computing shifted from a lab curiosity to something approaching practical reality. In November 2024, Microsoft and Atom Computing announced they had successfully created and entangled 24 logical qubits, a technical achievement representing a major step toward building quantum computers that can actually solve useful problems. To understand why this matters, we need to talk about the difference. Classical computers from smartphones to supercomputers process information using bits, units that represent 0 or 1, on or off. Everything you do comes down to manipulating billions of these binary bits. Quantum computers operate on fundamentally different principles. Instead of bits, they use qubits. Qubits can exist in a superposition of states, simultaneously representing both 0 and 1 until they're measured. When you have multiple qubits, they can represent exponentially more information. 2 classical bits can represent 4 possible values, but only one at a time. 2 qubits in superposition can represent all 4 values at the same time. A quantum computer with just a few hundred qubits could theoretically perform calculations that would take classical supercomputers longer than the age of the universe. But there's always been a catch. Qubits are extraordinarily fragile. They lose their quantum properties, a process called decoherence, when they interact with their environment. Temperature fluctuations, stray magnetic fields, can cause errors. This is why quantum computers must be cooled to near absolute zero. Even then, errors accumulate. The breakthrough that makes 2024 and 2025 so significant is progress in quantum error correction. Creating 24 logical qubits means creating qubits that have built-in error correction, making them far more stable and reliable. The race to build practical quantum computers is now global. In early 2025, Japan announced a $7.4 billion investment in quantum tech. Spain committed $900 million. Total public financing is beyond $10 billion. The private sector is equally invested, with Google, IBM, and Amazon pushing the boundaries. Beyond the engineering, there's something almost philosophical about quantum computing. These machines are harnessing the native language of the universe to solve problems. One of those problems is understanding and controlling nuclear fusion. On the 12th of February 2025, scientists at the West Tokamak reactor in France set a new world record. They maintained blistering hot plasma for 22 minutes and 17 seconds, surpassing the previous record by over 4 minutes. The plasma reached 50 million degrees Celsius, roughly 3 times the temperature at the core of the Sunday. Creating and controlling a star-like process on Earth is one of the most difficult challenges in science. Fusion works by forcing atomic nuclei together so tightly they merge, releasing energy. In the Sun, immense gravity does that. On Earth, we lack that advantage, so we need even higher temperatures, and we need a way to contain that hot plasma without it touching any material. The solution is magnetic confinement. Tokamaks use powerful magnetic fields to create a cage of force, holding the plasma in a donut shape, suspended in a vacuum. The 22-minute achievement by West is significant because future fusion power plants will need to operate continuously. You can't economically generate electricity if your reactor has to shut down every few minutes. This record, just weeks after China's East Tokamak's 17-minute record in January, shows that the engineering challenges of steady-state operation are slowly being solved. The private sector is also booming. ETA Technologies announced a major simplification in their plasma formation in April 2025, removing complex hardware. What makes fusion so tantalizing, despite the challenges, is the promise of nearly limitless clean energy. The fuel deuterium can be extracted from seawater, enough to power human civilization for millions of years. Tritium can be bred from lithium. Fusion produces no long-lived radioactive waste like fission reactors do. It produces no carbon emissions, and a fusion reactor cannot melt down or explode. The question is no longer if fusion will work, but when it will become practical and economical. Optimists point to the early 2030 seconds. Skeptics note that fusion has been perpetually 20 years away for 60 years. But the momentum in 2025 feels different. For the first time, it seems plausible that a child born today might grow up in a world where fusion power is as common as solar panels. And perhaps that child's generation will use fusion-powered spacecraft to explore the solar system, following the trails of those ancient comets and asteroids, and investigating the planets and moons we've only glimpsed from afar. One of those, Mars, continues to surprise us with hints that it once might have hosted life. In July 2024, NASA's Perseverance rover drilled a core sample from a rock nicknamed Chava Falls in Jezero Crater. The rock showed features mission scientists described as the most puzzling, complex, and potentially important they had encountered. After a year of rigorous peer review, the findings were published in Nature in September 2025, and they represent the strongest evidence yet that Mars might have once been home to microbial life. The key word there is might, because one of the hardest lessons in astrobiology is that nothing is ever as simple as it first appears. Chava Falls sits in an ancient riverbed. Billions of years ago, water flowed through this area, emptying into Jezero Crater, which was a lake at the time. The rock itself is sedimentary, made of clay and silt, exactly the kind of material on Earth that preserves fossils and chemical traces of ancient life. Perseverance's instruments detected organic carbon, sulfur, oxidized iron, and phosphorus, a combination that on Earth often indicates biological activity. But what really caught scientists' attention were small features they call leopard spots, tiny specks enriched with iron phosphate and iron sulfide scattered through the rock. On Earth, when microorganisms consume organic matter, they often produce iron phosphate and iron sulfide as metabolic byproducts. But here is the problem. Chemistry can also create similar patterns without biology. Hydrothermal processes, volcanic activity, all can generate iron-rich mineral deposits. The challenge is distinguishing between biological and non-biological origins, especially when you're doing it remotely with instruments on a rover millions of km away. This ambiguity is why scientists use the term potential biosignature rather than claiming they've found evidence of life. It's a conservative, deliberately cautious approach, because the claim that we've found extraterrestrial life requires extraordinary evidence. What makes this finding particularly intriguing is the age of the rocks. They are relatively young, geologically speaking, younger than many of the ancient rocks Perseverance has studied. This suggests Mars might have remained habitable for longer than previously thought, or that habitable conditions returned at later periods. The sample, officially named Sapphire Canyon, is now one of 30 samples Perseverance has collected and sealed in titanium tubes. The ultimate goal is to return these samples to Earth. Bringing them back would allow scientists to analyze them with instruments far more sophisticated, instruments that can measure isotope ratios, search for amino acids, and examine mineral structures at the atomic scale. Until then, the Sapphire Canyon sample sits in Perseverance's belly, a tiny piece of Mars containing what might be the most important discovery in history, or might be nothing more than interesting geology. In 2024, the average company spent $1.9 million on generative AI initiatives. Yet, less than 30% of AI leaders reported that their CEOs were happy with the return on investment, ROI. This disconnect reveals something important about where we are in the AI revolution. The technology works, sometimes spectacularly. But translating that capability into business value is harder than the initial hype suggested. 2025 is the year of that reality check, pushing companies to move from experimentation to focused deployment. The capabilities themselves continue to advance at a startling pace. In September 2025, researchers at Microsoft announced a breakthrough in protein simulation using an AI-driven system. Proteins are the molecular machines of life. Understanding how they fold is crucial for drug discovery. This AI allows researchers to simulate their dynamics with unprecedented speed. This isn't the only way AI is transforming science. In neuroscience, an AI model called Cell Transformer created one of the most detailed maps of the mouse brain ever produced, identifying 1,300 regions and subregions, including previously unknown areas. It works by analyzing massive data sets, mapping which genes are active in which cells, allowing the AI to identify boundaries humans might miss. AI isn't just accelerating research, it's becoming embedded in everyday tools. Gartner predicts that in 2025, 75% of enterprises will transition from AI pilots to full-scale operations. AI agents, autonomous software entities that can perceive, make decisions, and take actions, are moving from concept to reality. These aren't the chatbots of 5 years ago. These are systems that can handle complex tasks, like analyzing legal contracts, managing supply chains, or writing and debugging code. The rise of AI agents raises questions beyond technology. If an AI agent makes a mistake that causes harm, who is responsible? In late 2025, a lawsuit in Colorado highlighted these issues when parents claimed an AI chatbot had contributed to their teenager's suicide by simulating emotionally manipulative conversations. The case could become a landmark in determining liability. The next generation of AI systems will need to address these limitations. Current large language models don't understand what they're saying. They lack common sense. They make factual errors. They can produce outputs that seem confident but are completely wrong, a phenomenon called hallucination. Some researchers believe the path forward lies in composite AI, integrating multiple specialized models. Others think the breakthrough will come from integrating AI with robotics, giving it a body to learn about the physical world. Whichever direction AI takes, it's clear we are still in the early stages. The excitement is justified. The potential is real. But so are the challenges and risks. For nearly a century, cosmologists have believed the universe is mostly made of things we cannot see. Ordinary matter, the stuff of stars, planets, and people accounts for only about 5% of the universe's total mass energy. Another 27% is dark matter, invisible but detectable by its gravity. The remaining 68% is dark energy, an even more mysterious force speeding up the universe's expansion. But what if they don't exist at all? In October 2025, a paper by Rajendra Gupta, a physics professor at the University of Ottawa, proposed a radical alternative. Instead of filling the universe with invisible particles and unexplained energies, Gupta suggests that the fundamental forces of nature, like gravity, are slowly weakening as the universe ages. If this is true, the phenomena we attribute to dark matter and dark energy might be illusions, artifacts of us using constant laws of physics to describe a universe where those laws are gradually changing. The idea is both simple and profound. It could make distant galaxies rotate faster than we expect, mimicking dark matter. It could also make the universe's expansion appear to accelerate, mimicking dark energy. In this model, you don't need exotic, invisible substances. The timing of this proposal is interesting, as it coincides with other observational hints that something is off with our standard model. Data from DZ, released in April 2025, suggests dark energy may not be constant. It might be weakening over time. Meanwhile, experiments searching for dark matter particles, like the Lux Zeppelin detector, continue to come up empty-handed. But abandoning dark matter and dark energy isn't easy, because they explain so much. Any alternative theory needs to explain all of these phenomena. What makes this debate so fascinating is it touches on the most fundamental question: how do we know what is real? Dark matter and dark energy have never been directly detected. We infer their existence from their effects. Could we be making a mistake, like ancient astronomers adding complex circles to save a geocentric model, when the real answer, ellipses, was simpler? The answer will come from more data. The Vera C. Rubin Observatory, expected to begin observations in late 2025 or early 2026, will survey the sky with the largest digital camera ever built. The data it collects will test these models with unprecedented precision. Either way, the process reveals something beautiful about science. It is never finished. While scientists debate the cosmos and engineers build quantum computers, another, quieter revolution is happening. On the 8th of October 2025, Blue Origin launched its 15th space tourism mission. The passengers experienced a few minutes of weightlessness, saw the curve of the Earth, and returned safely. For them, a life-changing experience. For the space industry, it was business as usual. This normalization of access to space is significant. A generation ago, spaceflight was the exclusive domain of governments and professional astronauts. Now, private companies are flying paying customers. SpaceX has revolutionized launch with reusable rockets. Blue Origin is developing its own. Other companies are developing space planes, orbital hotels, and lunar landers. The infrastructure being built today isn't just for tourism. It's laying the groundwork for a future where humanity is a multi-planetary species. SpaceX's Starship, the largest rocket ever built, is designed to carry cargo and people to the Moon and Mars. NASA's Artemis program plans to return astronauts to the lunar surface, establishing a sustained presence. All this activity raises the question of why we should do this. The pragmatic answers include resource extraction and ensuring the long-term survival of humanity by spreading beyond a single planet. The more aspirational answers point to human curiosity and the drive to explore. Space represents the ultimate frontier, and space exploration doesn't happen in isolation. Quantum computers might one day optimize spacecraft trajectories. Fusion reactors could provide the power for fast propulsion systems, reducing travel time to Mars from months to weeks. AI will be essential for managing complex life support systems. Everything connects. We began with an asteroid that passed unnoticed and a comet brightening in the sky. We looked at a distant planet forming moons from a disk of dust. We saw quantum computers reaching new levels of sophistication and fusion reactors, hinting at a future powered by stars. We examined a rock on Mars that might hold evidence of past life. We watched AI map brains, simulate proteins, and raise new questions about responsibility. We considered proposals that dark matter and dark energy might not exist at all, and we noted that space travel is quietly becoming more accessible. Each of these developments carries uncertainty. Quantum computers might hit obstacles. Fusion might prove harder to commercialize. The Martian biosignatures might turn out to be geological. AI might plateau. But uncertainty is not the same as futility. It is the space where discovery happens. Science is not a collection of facts. It is a process, a way of asking questions and refining answers. And the questions we're asking now are among the most profound ever posed. What is the universe made of? How did life begin? Can we harness the power of stars? Are we alone? These questions don't have simple answers. And that's okay. The value lies in the search itself. The breakthroughs of 2025 inches quantum, fusion, Mars, AI, cosmology, and space access aren't separate stories. They are chapters in a larger narrative of human capability and curiosity. If fusion becomes commercially viable, energy abundance could transform civilization. If we confirm biosignatures on Mars, it would be one of the most significant discoveries in human history. If AI continues to advance, it could become a partner in scientific research. But these possibilities also come with risks. Technology is a tool. Quantum computers could break encryption. AI could reinforce biases. Navigating these risks requires more than technical skill. It requires wisdom, ethics, and foresight. That challenge belongs to all of us. So, here we are in October 2025, watching comets, reading about quantum entanglement, learning of plasma records, and potential biosignatures. The universe continues its ancient dance. Life, at least on one small blue world, has learned to look outward and ask questions. Thank you for joining me on this journey. If you enjoyed this exploration, consider leaving a like and subscribing. Keep looking up, keep asking questions, and remember that we are all part of this grand unfolding story.